Right, so welcome to Applied Computation Modeling, MG6039. So today, if we go to model, you find we are still under the FEA single part topic. Last week, we did the mesh convergence and mesh control. Today, we will do again. We have an activity about that, but first we start getting started single part exercise, and then you upload your answers here or your model under that forum. And then you do another one is Higgs key analysis. And then you have a question is about week 3 stress concentration and mesh control. You upload there. And if you have time, we can go and add more tutorials. Train, make you really fast and good in using the FEA analysis. So when you click on that, getting started single part exercise, you will see the information. A steel support track is attached by 4 screws at a wall and loaded by compressive load, similar to those brackets we have here for the markers and the racer, like you can see them. This one, similar to this. But this one has 4 screws, this one has 2. Same thing here, you can see them. Enough brackets. The Young modulus of the steel is 210 gigapascal and Passion ratio is 0.33. The yield stress is 650 megapascal. The applied load is 1.5 kilonewtons. Assume the attach as the wall screw interface is rigid, so you need to assume how you will fix it towards the wall. So those screws, how you apply the fixed support. Therefore, we'll be assuming that the displacement of the inner surface of the holes in all directions is 0. Compare displacement and maximum von Mises stresses for 2 meshes. So you try the coarse mesh, which we learned last week, and the fine mesh, and then determine the factor of safety for this load case, which I'll show you again. Now, how do I find the model? The SolidWorks part file is attached here. As soon as you click on here, it downloads onto your computer. Make sure, again, you create a folder. It's best to be on your desktop. Don't use the cloud because the cloud can generate different results for you. And start creating that folder. Call it with the name, the support rack exercise. And then start applying what we have done last week. Technically, you'll repeat everything now by your own, and I will come and check and help you if you needed help with it, okay? So you're not doing the part, you're just analyzing it, okay? And understanding how you apply the FEA. And then later when I have time, I'll show you other questions comes from industry. I'll pause the recording because we're not doing any activity. So what we did early is week 3, getting started a single part exercise, which I would do it now. A steel support rack is attached by 4 screws at the wall and loaded by the compressive load. So compressive load is added on that face. The Young modulus of the steel is 210 gigapascal and the Poisson ratio 0.33. The yield stress is 650 megapascal. The applied load is 1.5 kilonewtons. Assume the attachment at the wall screw interface is rigid. So we need to understand how this works. Therefore, we'll assume that the displacement of the inner surface of the holes in all directions is 0. We want us to compare the displacement and maximum von Mises stresses for 2 meshes. We use coarse mesh and the fine mesh, and then we determine the factor of safety. The model is here, so the difference between last week and this week's session, we are not redesigning the part, it already exists here. So as soon as you click here, we'll go on your download. I already started my SolidWorks 25, so I will open the model. I go to my downloads, and it just has a name. Just hiding these things. Open, and then I get the brackets. All right, so this one. If you first time doing FEA or forgot how to do it, that's what we start. First on, I need to ensure, I'll just move this here. I need to ensure my FEA is active, the simulation here. So if it's not active, I just come to add-ins from that gearbox. And then from the add-ins,
You have the SolidWorks simulations active on both sides. Shivam, can you please make your phone silent? Thank you. And we start with a new study, static study. And based on the model is giving to us, we need to set up the following material properties. And we have 1.5 kilonewtons load applied, and the fixtures, we show you how to work on them. So this is the model. Apply materials. This is a materials for an existing, but because it's a steel, we can find something very similar to that, any one of them, and then we can change the properties to match. So I can see that is the Poisson ratio is different. So I will copy this material. I come to customize. Under customize materials, I could just make a new library, call it steel. And then under that library, should be allowing me to add a new material. Control V or new library, open library, and steel, open. Now I have the steel. It doesn't. Okay. New category, steel. And then from that category, I will paste the material which I copied earlier, which I copied from the original library. I will just F2 or just name it, call it steel as second one or two in case they're interfering with the other steel value. And then when you click on that material, I will go back to the question. Wants Young modulus to be 210 gigapascal. So I could choose that as 210 already gigapascal. And the Poisson ratio, it's stated in the question, is 0.33. So I will retype that one to be 0.33. Shear modulus, I'll keep it the same. Mass density 7900. Tensile strength, I'll remove that or keep it the same. But the one is most important for me is the yield strength, which is given to me in the question, which is 650 megapascal. 650 E6. Okay. And 210 E9, the giga, just to make sure I'm using the right units. And 0.3, and I will leave the rest as it is. When I'm happy with everything, I just save and then apply. The save because I created the new material. And then when I see applied, I see that the name next to the part is there. I'm sharing my screen or not? I think I'm not. If you cannot see my screen, please ask me so I can.
You are.
No, you do. Yeah.
Okay, I was. Okay, good. Thank you. So now you see when I did that created new material copy. So what I will revise this to show you how I did it. I first search steel and any existing steel material. I choose any one of them. Very simple. Right click on it and copy that material and then exit that and then remove steel from it because it's still under the search. I go to customize material. I created a new one called steel. Did I lose it? Where was it? Here. I thought I did it. A new category you add, and then you can see the old category. You can call it steel 2, for example. I'm just redoing it. Or 3 in case. And then from that, you just right click and you say paste. So that will bring you whatever material. Since I didn't copy anything, I will copy the one I just created here. Copy, and I come here, and then I say paste, and then you see the materials come again. Not happy with that material, I can change the name here by double clicking, or I can change it here as well. So I call it steel 03. If in case I want to use another customized materials. Happy, you save, and then apply. And then you can see it's changed now from steel 02 to steel 03. That's in case you want to do it. By default, because I used to do different projects, I created cork materials for a helmet project or different materials, and you can customize any material based on your project you're working on. And please, if you have any questions, just feel free to ask me. All right. After I've done the materials, and now I will set up the fixture, right click. But before setting up the fixture, one thing I don't like about working with that gray, so I use the plain white background, and maybe we can show the geometry so you can see it clearly instead of just that. And also, I'm not really interested in real view graphic. I just want a normal graphic view. And so I deactivated these things by default. Fixtures, fixed geometry. Based on the question, it says to fix around the hollows of those screws. So I'll use surface 1, surface 2. And you see when I'm selecting, they're showing here phase 1 and phase 2. Phase 1, phase 2 for the other one. And you can see I selected this. This type of fixed geometry is not a roller, it's not fixed hinge, because hinge give you that mechanism to hinge it. Happy with that, click OK. You can see the green indicates where it's fixed now, kind of fixed to the wall. External loads, right click, apply forces. I will go back to the question. It says I need to apply 1.5 kilonewtons. So I come back here. The direction based on the question, it's indicated to apply the load here. You cannot see it, the image is very small. So you apply a compressive load here. So you come, you select that face 1, it's going downwards. If the load was going different direction, you reverse it. If you want to go, it's upwards. But in my case, it's going downwards. So it's against the y-axis. And that value is not kilonewtons. So I have an option to write 1.5 kilonewton and then click enter, and it doesn't give me the value. So either you change the units here, link a value, or 1,500. Sometimes if I want to change the units after finishing here, you could close this and come here and change the system units instead of millimeters, grams, seconds to maybe meters, kilograms, and second. And you can do it anytime. And then as soon as you it's required you to apply the load, force load, ask you where do you want to apply it, and then you can change the value. But now it's already there. So I'll go back to my millimeter system units. All right, so before I forgot, very important for you to save the project. Save as. And when you save it, because as I said before, FEA generates a lot of questions and answers and solutions for you. So for me, I would save it on desktop because this is not my computer, and I will delete everything at the end. I'll create a new folder, must be a new folder. I will call it the question which came here. It's the steel support rack, and F2, and then double click on that, and then save. Save, and now you see it's updating everything in it. Force 1,500 was just not reading, playing funny. Selected entity, okay. Just in case the force was not there. Okay. Now the mesh. Please, if you have any questions so far, ask me. I'll pause. Feel free to ask. So I applied external load on that face. I fixed these faces for the screw. And then now I need to apply the mesh. So the question is telling us the following scenario. Compare displacement and maximum von Mises stress for two meshes. One we do chorus mesh study, and the second one fine mesh study. And then we determine the factor of safety for this load case. We didn't do a factor of safety last week, so we will learn it today. So mesh, right click, create mesh. And then from it, I will go to that end as a chorus. later, by time I'll show you, can we go and do more advanced meshing, but now we're just going with the basic method course. And I'm happy to, just moving this pointer here, it's a bit in the way. And then I click OK. Will take shorter time, we'll create that mesh. I can see it is not the best mesh. I will call this static study. I'll call it the first example, which of first study chorus mesh. Control C, F2, just F2 or double click, you can get out. Now, since I'm happy with the mesh, based on the requirements of the question, I'm not specifically happy with this mesh. It's the worst mesh in my opinion, but we trying to improve it. Come here, run the results, and it's telling me this result is being solved. All right, so let's try to organize some nice stuff. For some reason, my model didn't choose my material, and I'll tell you how did I figure out that. We check that. So first, you double click on this von Mises stresses. It will show me the definition I need to change from that unit to megapascal. And I go to chart option. I may change it from scientific to floatings to remove that big numbers. When I click megapascal, it's nicely to read the number 318.42 megapascal. If you see the yield strength is 710, and in the question, the yield stress is 650. So I figured out I had some issues done and I didn't pick it up. So I come back here and I say apply material. What did happen to my geometry? Because by mistake, when I did some changes, I didn't adjust that. So I will go back to my original material, which is 650. I say apply, close. Now I can see steel 03. I readjust that and run the study again because I must see here the right yield strength materials and still is not giving me the right value for it. So I would check again if I have something wrong I followed. Applied load, what's the yield stress 650. So I would check again if something, I change the value. So this is kind of like if you want to check here, if you see here, I put that value in the wrong place. It should be here. Apply. And that's everything. So it's a way to understand what we're doing. It does make sense. And like you can see is like why I'm getting an answer is not matching what I'm anticipating. So now I can see my yield strength is 650, which is the acceptable range for this example as giving to me. Why this is important? Because if that arrow appears in here, anywhere here, it's mean my material felt with that chorus mesh, and it's mean the brackets will break at certain location where it's showing high values for this von Mises stresses. So I could copy this. The maximum is 313, and I generate a PowerPoint. I'll show you later when you can upload. But at the same time, I double click on the displacement. I can see it. Again, I'm not happy to see this, so I make it as a floating system. So double click, change from scientific to floating, and you can change how many significant numbers you want to see. 3 is nice. So the maximum displacement is 2.96 millimeters, because my system is in millimeters. And then I can click on strain if in case I'm interested, but it's not required in this question. I'm just showing to you. Change from scientific to floating. And that one, maybe 3 significant figures is not enough, so I'll show more because the strain is very small. It is dimensionless. It's millimeters divided by millimeters. Now, the other things required in this question, I go and revisit the question. I did the displacement and maximum von Mises for the chorus mesh. Now I would do the factor of safety for this load case. So come back here, factor of safety, results, right click on it, define factor of safety plot. You can see it here. And it would tell me all bodies. Yes, sometimes you can do selected bodies. That's when you have a multiple part. You want to use the automatic method or the von Mises stress method, or you can use the Morse circle, which you land in strength of materials, or maximum shear stress, which is the other topic you learned in materials. So you can use automatic. Let's stick with automatic at this stage. Pay attention here. You can set the upper limit to 3 factor of safety. And here you click on that arrow next. It asks you multiplication factor. I'll skip it 1. And then factor of safety distribution areas below factor of safety 1, which is giving me the factor of safety for this model is 2.073. As soon as I click that, I go and click here to make it again floating. The scientific doesn't make any sense. So my factor safety, it shows the maximum in red. Don't read the blue ones. You read the red areas is 2.074 for the stresses at these hot spot or the red spots based on the color. Color coding FEA analysis and CFD is very important. When it's red, it means high stress, blue is less stress. So based on that, it's showing to me that these the area where I anticipate the material could fail, but not with this scenario, with this load. It could fail when that load increased more than 1,500 newtons. I'm happy with this result. I go back again to stresses. It's 313 for coarse mesh. Now I want to do the fine mesh. But please feel free to ask if you have any questions. Especially Josiah, Glenn. Nice to see you, Glenn. And Brody. If you have any question, feel free to ask, please. All good. All right, let's continue. So now for the fine mesh study, right-click on the coarse mesh here and copy study. I will call it, change the name, call it fine mesh. And then click OK. Now I'll repeat everything. The material is set up. And you remember I fixed it. I had a few issues with it. I managed to fix it. Fixture is the same, so no problems. The load is the same. Now, the only things we need to create a new mesh. Create mesh. Now, instead of leaving it at coarse, we go to the other end, fine mesh. And the difference between them, coarse, the element was around 20 millimeters, 0.86. But the fine mesh is 5.2. And by the way, this is not the final. We can even decrease it less than even that number, but will take longer time to process. So when I click OK, the computer starts taking longer time. That's what I needed for the first coarse simulation, and then start creating for me more acceptable mesh. Definitely what we did last week, we could use control mesh to make it even better around the edges and around this hole or the other holes interest. And now I'm happy with this mesh. I would just say run this study. And I'll wait for the computer to start running the study. My advice for you when you're running FEA, CFD analysis on your computer, don't bother it. Get another computer and do other things if you're waiting for it. Because anything could disturb the processor or your memory card or your RAM. It could disturb the process of solving the simulation if your computer is not high spec values. Right, so again, von Mises. Again, I always go to definition, change the units to megapascal, and you go to the chart, change that to floating, so you can see the values clearly. And you can see my yield stress is 650. I use the right material. The maximum stress is 359. Compared to the other study was 318. So the better the mesh, you get the most accurate results. For displacement, I repeat the same thing, and I try to make it floating to see the number clearly. It's 3.342. I record that nicely in a PowerPoint or Word file, and then you attach it. I'll show you where you attach it. And then the same thing, we go and try to generate this factor of safety. So right-click on results, define factor of safety plot, all bodies, automatic method, set that to 3, click here next, leave that multiplication factor of 1, because this, if you have more application required, a higher factor of safety, then you always follow that. Factor of safety will be 1.8. So when we got the mesh even better, the factor of safety, it's became 1.809. So I changed that to make it floating again, so you can see the numbers nicely. So the 1.80, which is the factor of safety for the fine mesh study. So that is kind of like how you create the study for it. Believe it or not, some companies, they ask you if you apply, for example, companies similar to Caliber Design, they may ask you after the second interview or in the second interview to perform this type of simulation, and then they give you a multi-choice hard-written answers to write the value of your factor of safety and your von Mises stress, maximum stress value. And then they will come with another things, how can you suggest to improve that as well? That's one of their job interviews. So it's very common to get that if you're working in the FEA analysis, if in future, if you work in it or you do some study abroad. Time for questions. Please let me know if you have any questions here or online, people. And again, this recording would be posted on Moodle as well to make everyone think. So that is for the students. Sorry again for the WIT students. I didn't know that it's set to 11. But definitely I'll fix it after this session to make it 10, because we start 10. And if you have anything, please just email me. I'm online like during that session, so I can fix it very quickly for you, because I could send you the code for the meeting and then you can join it. You don't even need the permission. So that was the code. You can keep it and then you can join at any second. So if you have anything, just email me quickly, or through Moodle, you can message me. That's the quickest method for you. All right. Any questions? Here, online?
Nope.
Awesome. So now, especially the WIT students, you can upload, you can retry this by your own time. And, exit. I'll tell you where you upload that. So you come to that session, is the week 3 here, and you can see the Wintech students already started uploading this attempt. So you add discussion. I'll show you example. You type the topic, click on advanced. So when you click on advanced, will allows you to upload attachments. So that attachment is mean your answer for this question using PowerPoint or Word files to demonstrate you done the topic. Okay. All right. So if you find this topic is really good, I now ask you to follow the instructions for week 3, the hex key analysis. Open that link, and you have here complete the following static analysis SolidWorks. So you can access this hex key, which is the PDF file, explaining you the process. And then here, SolidWorks part, you click on it, you will open it through SolidWorks and follow the instructions. And for the people online and the people here, the online, you can share your screen with me, and here ask me if you need me. So you post your model answer, so you add the discussion. I will give you time for it till we finish it, and then we'll tell you what's next. So I'll pause the recording because this is the time just for asking questions. Finish this question. This is kind of like the coarse mesh study or even the fine mesh study. And again, just to show you the factor of safety, this one, it's about 1.575. If you want to calculate the list resultant force, you just click here and then you update and you find the value, and you can save that value as well for you. The other things I want you to do today, which is an exercise for you, because we're almost done, but you can start with it now. So what is this exercise? You go to the section 3, what's that section of FEA single parts, and there is a PowerPoint I generated for you, which I want you to work on it. My internet's slowing, I think because I use too much of the work in it. So after you upload the hex key analysis, come to week 3 stress concentration and mesh control. So now kind of we sum up what we have learned from last week and this week. So stress concentration, you can download this PowerPoint, and you need to design something to study. It's kind of fatigue, but no fatigue. How much is the stress concentration for this piece or this part? It's made of material ASTM, A36 steel. So compare the calculation of load applied on the following part made of material ASTM, A36 steel. You can search that. You can find the material, so you don't need to create it. The part is fixed at one end. So it's fixed at that end. That face is fixed. And also a load applied at that end with a value 22,241.108 newtons, as shown in this figure. You need to draw this exactly starting from front plane and then mid plane to extend it with a value. By the way, if these are small for you to see, feel free to enlarge them. So when you extrude that plane, use the value 12.7 millimeters, and you extrude it mid-plane, okay? So you can just enlarge that. And then you need to create that circle. That circle you just extrude through, as showing here, but with that diameter, so you can get it through to create that. So if I ask you from mechanical engineering perspective, strength of materials, where are the weakest points for this parts and shown in figure 1? Where do you think that any break or any failure of materials will be happening?
The shaft, like we had the corners there.
So that's corners here
No.
and the circle as well. Circle is number 1. It's the top one. Here we anticipate to have high stress values, von Mises stress. And here as well. Why are we saying here? Because if you see the diagrams I'm giving you, we need to calculate the K value, the correction factor for that stress concentration. So you will have the first relationship is the R over D, the radius of the circle divided by the D. The D is the width of it. And then you intersect with that line and you read the K value. And then you calculate what? You have the load divided by area. You calculate the stress. What is the load? Is the one giving 22,000 newtons divided by the area. Which area will be the front area for that one? So the area here for that will be very interesting area. It's the rectangular shape minus the radius or the diameter, because you have a hollow inside. So that area will be a cross section here. And then you calculate the value and you compare between what you get from the FEA analysis and what you would do in the calculations. Then at those fillets, also it's recommended to check that because it's the second weakest area, not the first, second. So the relationship you find first, R over D. R is the radius of the fillet. D is that distance. And then you intersect with one of these lines. These lines is D over D. So which D? That dimension, the longest, like the longest one, divided by what? By the small d, this one. And then you intersect with one of these lines to read the K value, and then you apply to mathematically to calculate the maximum stress. So you generate a table. One is fine mesh calculated by FEA. One is calculated by your Excel files or your calculations. And then you compare between the calculations and the FEA and see the error. You need to find the error. So what I did for the error, there are many things. You can get the bigger value minus the smaller value divided by this biggest value times 100%. That's an error to find the difference between them to validate your design. So since we have a few left time, 20 minutes, you have two options. If you're done with the hex key, please finish it and upload. If you upload it, then you can start working in this stress concentration exercise. If you're still on the hex key, then focus on the hex key and submit this during the time. So I need to see it before we start next week. Yes, it's homework. The reason we're doing 3 hours, not 4 hours in class, because I make you to do a lot of work at home. Self-study. So, and they have points in your assignment 1, which I will talk about it in the last 10 minutes. Assignment 1 is due in this month. Need to be aware of that as well.
pretty much gonna be similar to this. You'll probably have a beam goes out, you calculate it, and then you measure. Pretty much probably be like a lab anyway, right?
Yes, it's a lab, but you design the lab. So now I'm showing you many different designs. So you work in a group. These are for you guys. Don't lose them. If you lose them, no replacement. And you work in a group. And these are for you guys. I'll talk about them when it comes. So in the last 10 minutes, we'll talk about the assignment. Because the assignment, and the people from which I need to send the instruction to GEL to get you the material for the lab, or we find alternatives if it's difficult to get the material. So I'll talk to you first, and then we see how can we communicate to GEL to support you with that. So again, if you're working on the hex key, please finish it now. You done the hex key, start working on the stress concentration. So now the last thing I need to introduce you is the assignment. So if you go to your course outline, your assignment 1 is due on the 25th of March, 11 p.m. You submit the report and the proper file. So the assignment is always kept under course outlines, such as I mentioned earlier. Everything is available under the course outline, your assessment and everything we're doing in this course. So you come here to page 12, and assignment 1. I would go through it by details. Just let me move this up. So comparing real-world measurement FEA, report and SolidWorks files. 30% is the weighting of this assessment. 50 marks is the total. You will follow the following learning outcomes. Use and apply mathematical software package to solve problems. Use and apply computer-aided design analysis software package for stress analysis and computation fluid dynamics. Here we do the stress analysis, and assignment 2 would do the fluid computation, because one is solid, one is fluid. And the last thing is the project. How can we combine them together, which to use them? And then use spreadsheets. So when you get the results, you need to present them using spreadsheet. So when you're comparing different meshes and different values, you can present them in an Excel file. And I'll show you some calculations using Excel files in some of the weeks later. But in this one, you just process the result with using Excel sheets. All right, so the assessment. It's just explaining the essential of CFD modeling and going through it. But I have a camera, so for Roddy is here only. So because it's winter, I didn't know that Wit will join this class, so I was not prepared for that. So we have a material which is made of Arclide or plastics. We give a different designs for the students. And for example, if you see these two materials, I know it's transfers, so they have almost identical dimensions. However, the middle one, they look differently. One is a circular one that way, and that's design of it. So similar to what we were doing in the stress concentration, but here is different. What is the difference? You need to design the experiments to break them. And then you do the FEA analysis. However, this is not wise way. You do the FEA analysis first, and then you design the experiment so you can compare the result to see if this is what you can do. Some of students, I'll show you next session how they do examples of cantilever. So they fix it on one end and they apply load at the other end. And then when it breaks, the CFD analysis will predict the location of the weakest area, because there are multiple weakest areas, similar to what we've been doing today. But in this one, you don't know which one of them. You will say 90% is the middle one. But what about this one? When they are identical, do we still say 90% is the middle one when we just change the structures in the middle, comparing them? Okay, so that is the understanding. Now, you follow the guidelines for the report. you provide the title, paragraph to describe the problem, and then laboratory test. You design the experiment, is you. So be wise before you break them, because if you do an experiment, FEA SolidWorks is limited to do that simulation. I don't have parts anymore. That's why I cannot have any parts. And then you report the lab results, and then you start with the discussions. And then at the same time, you do the finite element results for it, and you compare between them using the APA referencing, complete Moodle lessons. That's what are things I say, please complete Moodle lessons. So we do 3 hours because you need to do extra after study to finish the things we've done in the class, because it's not enough to do them. And the other reason, because simulation, sometimes you stop because simulation takes 1 hour just to finish the task. You see it next week when we do assemblies. The results will take 30 minutes. You cannot do anything because you don't want to bother the computer. So many of the time, you maybe run the simulation at night and then you upload the result because you don't want to waste your time. You may need to do something else and study. But that's the simulation life when you work in FEA. And this is the marking guide and rubric for it, and you go through it. So if you go back to Moodle, you come under assignments, that tab, and you can see the waiting for it. Please, AI is not allowed, is prohibiting this. You get the assignment to submit the report to Turnitin file, and that should be 30, not 25. That's wrong. Yeah, I need to check that, change that. Wow, how did this happen? I'm on the right Moodle? Yes. Damn it.
As a group? Or
Yeah, as a group.
so even a report would be a group.
Group would be reports. Yeah. Oh, it's okay. You can take that side. Yeah. And here. Yeah. All good.
Yeah, I'm sure.
I thought this one is fixed. I'm surprised it's not fixed. Someone unfix it. So all the submission would be 11 p.m. and 29th of April. How this didn't fix? The only one is during class, which is this one, the 40%. And you 11 a.m. presentation. Yeah, presentation will be for you guys online, the with students, and the rest will be here in class. Yeah. So for the with students, I think it's only you, Roddy, which I need to rely on you, please. And I will email Jill and CC all of you. The materials are here in that file folder. You need to select 2 of these materials and different. So for example, each one of you to become in a group of 2 students. So group 1 would do sample 1 and 2, and group 2 would do sample 3 and 4. And then based on it, you just see the materials are the same, but they have different slightly changes in the middle. So for example, this is the material. You just need them to print them for them. So that is an option if Jill can print it out. If not, then I am allowing you to use any alternative materials as long as you keep the concept of the assignment is the same. So to make it easy for you, so you can use any material to test on it. What do you reckon, Brody? What's your suggestion?
Either way should work.
Yeah, so I'm happy if you come and propose a material by yourself, like as a group, 2 students per group. I'm happy with that, as long as you meet the specification. That's most important for me. Even if you find a hex key like this one and you do something, I'm happy with that. Do you get my point? As long as a single part.
Oh yeah.
Okay? Yeah. And then we'll talk more about it. I'm going to email Jill to make sure if she want to print it, if she had the budget for it, so it will be even better. If not, then you guys will move to more flexibility to make sure you achieve that. And that's all for today. It's the last minutes. If you have any question, I'll talk more about the assignments. Yeah.